Okay, thank you for the co-host, okay, to help me to admit all your friends into these sessions. Okay, all right. Okay, so on last week, okay, we have stopped at somewhere here, okay, about the first order transfer functions, okay. How should I say? We are doing, or we are looking at the time response for a first order transfer functions, okay. From that first order transfer functions, we would observe that sometimes we may need to do some testing, okay, in order for us to evaluate, okay, uh, whether or to get the kind of transfer functions for our modeling purpose. Okay, so we have measured so-called the time constant, okay, as well as the steady state value. Okay, so these two would be the important parameters, okay, that we can observe from a testing, okay, when we insert with a step input. Okay, so when we insert with a step input and when we observe for a first order transfer function, we would see that the graph would be a straight line. Okay, therefore we would take this so-called response, okay, to be modeled later on. Okay, so first we would like to get the a values, okay, which is based on this formula, all right. Okay, so you get that value, and then after we get the a value, then we will get the k value, okay, and then we insert into our original transfer functions, okay, that we have defined what is the k and a, all right. Therefore, we have formulate the transfer function for this so-called linear or the first order system. Okay, so you will see that it is a straight line over here and there is no oscillation, not sinusoidal form. Okay, so it just goes straight, okay, curve and turn to a steady state, right? So this is the characteristic of a first order system, right? So now today we would go into the second order system or second order transfer functions, right? But before we start, okay, just for informations, okay, as you know, we have collected a short survey on whether you can take the test face to face or not on 12th of November, okay, which is next Friday, right? So yes, we can see from here 69% or 29% has responded that you are able to come, right, to take this test. Okay, so therefore I think for this case we would do it like hybrid. Is it okay for you? Okay, means for those who can attend, you would attend it face to face. Okay, then those who cannot attend, you would do it online, right, for the first test. Okay, then slowly we move back to the original lah. Okay, if we are able to we are allowed to do the face to face fully in the later stage, then we would proceed with that. Okay, I know some of you may just back and you would have to do some self isolations, right? So therefore you may not able to attend and so on. Okay, so I understand on that. Okay, so for those who can attend, please take note that I will inform you the locations on where you would take the test in FKJ. All right. Okay. Okay. So for the test, it will covers until where we stop today. Okay. So our planning would be to finish off this second order system. Okay. The time response for the second order system. Okay. So we will cover until this particular chapter itself. Right. So as you can see now, right, this is the characteristic or the time response graph. Okay, you can see how when the time increase, okay, how it is responding, right? So we can see that there is a so-called oscillations, okay, in the sinusoidal form, okay, and we usually define this as a second order system, okay, because you can see that the second order system will show a wide range of response, okay, as such, okay. So for this particular form, okay, which will continue from maximum to the minimum to the maximum and back to minimum, and it will continuous like a sine graph, right? A sinusoidal graph, okay. We call this as undamped, okay, meaning to say it will continue forever like this, okay. No damping occurs, right? Then for the case where under dam, okay, then undam, then slowly we come to the under dam where it will slowly damped, okay. It will still oscillate, okay, but then after some time it will then being damped out, okay, to a steady state value, right? For a critically damped, now you can see that this critically damped characteristic would be something very similar to the first order system, okay. It goes up, okay, but it would not overshoot, okay. It will not go up and down, okay. It will just curve up and go to the steady state value, okay. So this is a critically damped characteristic, okay. And when we further increase the damping ratio, okay, which we will study later on, we will say that it's over damped, then you can see that the graph will be like this, okay. Again, very similar to the first order system, okay. But how we can distinguish whether this time response is a first order or a second order, okay, even though there is a similarity in between them, you have to look at the beginning, okay. So if you look at the beginning, okay, if you start with like this, okay, like a sine curve, okay, so it will curve like this, okay. Whereas for a first order system, it will just go up like this, right? So you can see that just go straight up, okay, straight line up, right? But for a second order, no matter whether it's over damped, critical damped, even though the characteristic after few milliseconds, it will start to behave similar to the first order, but then the starting point, you can see that is a slow before it's accelerate up, right? So this is the characteristics of a second order system, okay? So for this second order system, we have two poles, okay? As you can see from the graph itself, okay? We say upper one, if it is equals to zero, that is zero, right? And the bottom one, as we see second order system, we will have a second order polynomial, okay? And because it is a second order polynomial, we would expect two pools, okay? So two pools or two roots, okay? When we solve this, you will have two roots, right? Meaning to say you have two poles in that case, right? So a general two second order system will have two finite pools and no zeros. Okay, the terms, as we have defined previously, okay, is the scales of multiplying factors. Okay. Then what we can see that the unit start response can found using, as you can expect, okay, just R multiplied by G give you the C value, right? The input multiplied by the transfer function give you the output, right? So as you can see, this would be what we expect, okay? And again, usually we would test it with a step input. So to characterize any control system at the beginning, we will usually use a step input, right? So therefore, we will apply, if the step input, the input response would be 1 over S, okay? And followed by the partial expansions and so on. So eventually, we would get something like this, right? So you can see that this polynomial now, okay, as we find the roots, okay, it can be solved in this way, okay, meaning to say the roots would be minus 7.854 as well as the minus 1.1, right? So if we plot, sorry, if we plot this out, okay, therefore you will see that there is two roots. Okay, so two roots as we expected, okay, and you can also try to use the Scilab, okay, or MATLAB later on. Okay, you can try it on your own, right? Previously, I have shown you how to plot it using the function PLZR, right? So you just use that, okay, PL pool ZR0, okay, pool zeros plot, right? So you can plot it out and it will display something like this. Okay, and at the same time, if you would like to see the response, you can also use the XCOS, okay, to simulate it, right? So you may see something in this form. Okay, so the starting is curve, slow down, and then move up rapidly, right? So how to solve this one? I guess I do not have to uh, tell you how to write this one. You can solve this into this, right? Okay, you just use the formula, right, for a second order polynomial, right? Okay, so from there, we would notice that there is two roots, and that roots appear on the real axis. Okay, so the real axis, as you can see, when we plot the S-plane curve, okay, S-plane curve always start with an axis, and this is not X, okay, this is the sigma represent a real, and this J omega represent the imaginary axis. Okay, so we have real axis and the imaginary axis. Okay, and we will notice that two poles lies along the real axis. Okay, so we say that as a real poles. Okay, so this format or this characteristics of the pool system, okay, will give us what we call this as an overdam response. Okay, if we plot this out, this is the overdam characteristics. Okay, meaning to say, for an overdam system, overdam second order transfer function system, okay, it will have two real pools. Okay, two real pools. Okay, and the response of this would be something like this, right? So you have a constant, okay, plus k e to the power of your solutions, your roots, okay, plus your roots again, okay, exponential to the roots t. Okay, so this is how it would looks like, okay, for the output itself. Okay, so immediately you can see that the patterns keep repeating. Okay, by doing this, okay, by defining, categorize this second order system time response, okay, into four, and then under dam, critically dam, and over dam. Okay, and we observe how it respond to the system itself. Okay, we will not that by knowing the locations of the pools, okay, we can categorize this, okay, without plotting this, okay, without plotting the time response from only the S-plane plot. Okay, we already know, okay, what type of response we would expect. Okay, so this is the important things of understanding, okay, how all these things will affect, okay, the whole equations, right? Now for a second plot, the under dam response system, okay, we can see that for this particular equations, okay, for this particular equations, s squared plus 2s plus 9, okay, eventually if you intend to solve this one, you would get minus 1 plus minus j to the square root of 8. Okay, there is an imaginary uh, solutions or the root itself. Okay, we call this as a complex pool. Okay, so how it would looks like on the poles and zero plot itself is that it's no longer, the pool is no longer on the real axis but away from the real axis. Okay, so you can see that because this is a plus and minus, so plus minus, okay, so the real value is minus 1 and the imaginary value is square root of 8. So therefore you have to mark over here as well as the other side. Okay, so you can see that for an under dam system, you have two complex pole, right? Meaning to say the complex pole will appear not lying on any of the axis. Okay, as long as there is this component, it is not a real pools. Okay, and you expect the characteristic would be like this. Okay, under them. Okay, it will still damped out, okay, but then it's under damped, right? So call these sections as the sinusoidal oscillations of it, okay. And what occurs here, okay, because they still have this so-called real component, okay. So this real component representing or contribute to the exponential decay of this particular frequency, right? So this is what it means, the particular exponential decay of the real parts, okay? So it will so-called being damped, the maximum point will reach this particular line, okay, before it will goes down again, right? So here the time constant for the exponential decay is equals to the reciprocal of the real parts, okay, 1 over of the real part. Okay, so the value of the imaginary would be the frequency of the sinusoidal, okay, or we call it as a damped frequency of oscillations, omega d, all right, which you will see later on, and probably you may also see it in mechanical vibrations, okay. I'm not sure whether you have seen it now or maybe later on, right? So all these characteristics, as we first derive from the first week, right? We try to model our mechanical system using transfer functions, right? Okay, so from that particular system, you know that it can be a first order or second order or even higher order of a system, okay? And because of that characteristics of modeling itself, you would expect something similar, right? Similar of in terms of the response, okay? And the keywords that we will use later on will be something again similar, like time constant, uh, damping ratio, okay, and so on, okay, and also the damped frequency, okay, omega d, right? So this imaginary part represents the actual frequency of the sinusoidals, okay. And lastly, the steady state response is generated by the input, okay, and is known as the undamped response, okay, which contribute to this whole particular characteristics. Okay? So now, by looking at these examples, okay, now you have learned two form of second order, right? One is underdamped, one is undamped, right? Okay, sorry, one is underdamped, yeah, and one is overdamped, okay. So which would that be, okay? Can we solve this into like a real solutions or real roots, or there is a complex roots, okay? If you can solve this, okay, therefore you would notice that it has a complex root, okay, for this particular bottom side, okay. So once we know this has a complex root itself, we would expect this would be a kind of damping, which is we call it as under dam, okay, something like this, okay. So you just have to compare it back, right? And you would get the results. So once we get this particular form, okay, therefore this real parts still represent the exponential component, okay, the exponential decay of it, e minus 5t, okay, whereas this imaginary part, okay, would represent by the frequency itself, okay, how much phase it is away from it, okay. So you have to do a like bracket cos this value t, okay, minus your base, okay. So this would be your expected equations or expected time response equations, okay. So it would be very straightforward without solving it directly, okay, by only looking at the characteristic of the denominators, okay, the roots of it, okay, we would able to see what kind of response we would get. right? There also we would define this phi as the arctangent of K3 over K2 and so on, right? So you just have to follow it accordingly, right? Next would be the cases where we have the undamped response, okay? So how it would looks like, okay, when it would never damp, okay, for the particular second order system itself, you will see that this segment, okay, again, the denominator part will have two imaginary pools, okay, because from this, what we get is just plus minus J3, right? Okay, we don't have any real values, okay? The real values is 0, okay? So when there is no real values, okay, and you know that from previous ideas, we say that the real values contribute to the decay itself, okay? So this segment do not have any real roots, okay, for our denominators, therefore it will never decay, okay? So there is no exponential decay form, okay? It only consists of the sinusoidal part or the cosine part, okay, which is the cos 3. Since this is 3, so 3t minus the phi, okay? So remember, and then there is two complex pool, okay, that do not have the real parts, okay? Or in other words, the complex pool lies along the imaginary axis, okay? So it is on the j omega axis now, okay? So when you see this particular pattern, therefore you expect this system to be undamped, okay? We will never damp out, right? So far, what you have seen now is that all the roots, if you notice, it is on the left-hand side, right? Okay, all the roots on the left-hand side. Now it slowly move again, still on the left-hand side, okay? And on this particular undamped response, okay, it slowly move, okay, now to the 0, okay, still not to the right-hand side or the real values not positive, okay, all still negative or 0, okay. So from this characteristic itself, as you can see, okay, from the damped one, okay, to slowly undamped, okay. So what would you deduce, okay, if the roots is now on the right hand side of the imaginary axis, okay, if it is over here, what would you expect? Any ideas? Previously, over on this side, you would see that it's damped very fast, okay? Then slowly when we have a complex one, okay, but nearer, then it will still damped but slower, right? But when we have the roots on the imaginary axis, then it will start to oscillate, okay? No damping, right? So when you go further onwards, okay, in the next chapter, okay, when we discuss the stability, actually when these roots come to the right hand side, what would occur is that the system now become unstable, okay? Instead of maintaining the same maximum value, it will continue to become bigger and bigger, right? So that is the characteristic of the pool when it start to move to the right hand side, okay? Okay, so that we will cover later on the next chapter, right? But let's continue back to the characteristic of the second order system, okay? So here you will see that for a critically damped response, okay, the denominator over here will now have two equal real pools, okay? Instead of two separate real pools previously, now we have the same pools but two, okay, at the same value. Okay, so normally we just put mark like this lah, right, at the same pools. Okay, and when this occurs, we say that this is a critically damped response. Okay, and yeah, it's still the same, but you have to add a t over here, okay, because we have two same exponential decays over there. Right? So what we call, or why we call this critically damped response, is that this type of response is the fastest possible without the overshoot. Okay, so this is the characteristics of the critically damped response. Okay, so here is the summaries of what we have discussed. Okay, for over damped, we have two real roots, okay, separately. Okay, then under them, we have two complex pools separately, right? Undamped, okay, we have two imaginary pools, okay, without any real parts. Okay, and critically damped, we have two real roots, okay, at the same value, right? And these are the response of that. Okay, so any questions so far?
No, doctor.
No,
Okay,
doctor.
right, great. Okay, so you can try by inserting all these equations, okay, these particular equations. Okay, you can try it. Okay, and then you can generate this graph from Scilab or MATLAB. Okay, so this is generated from the Scilab itself. Okay, and I label it with undamped and so on. Right, so this is how it would looks like. Okay, the step response for this particular second order damping cases. Okay, next would be the characteristics, okay, of a second order system. Okay, as I've mentioned earlier, we would come to a point where you would use the terms like damping ratio and also a frequency. And here, as we would see, we would use the terms called natural frequency. Okay, so this natural frequency for a second order system is the frequency of the oscillations of that particular system without any damping. Okay, naturally it's already oscillating. Okay, assuming no damping at all, right? And then we will also have this damping ratio. Okay, to characterize the the damped oscillations. Okay, so two parameters. Okay, one is omega n and one is this sigma. Okay. Okay, so we have this damping ratio, okay, defined as the exponential decay frequency divided by the natural frequency. All right, and this is in radian per second. Okay, so if we would like to turn it into the second, okay, then it would be 1 over 2 pi natural period. Okay, period is 1 over frequency, okay, and divide by the exponential time constant. Again, you can see that the time constant appear here. Okay, so these equations will give us a relationship. Okay, when we able to get the time constant later on, okay, that would be a good parameters that we can insert into our equations to in order for us to know what is the damping ratio. Okay, so by comparing the damping ratio later on, we would easily know what kind of characteristics, okay, of the system. All right, so what we have covered previously for a second order system is by looking at the positions of the pool on the S plane, we would roughly know how is the response of the second order system. Okay, now what we trying to do is to see, okay, what is the relationship between the natural frequency as well as the damping ratio on the so-called time response again. Okay, so here we would start with the second order system equations. Okay, we have the general one, b over s square plus as plus b. Okay, generalized as a and b. So These two constant we assume as the same, okay, just like the first order system, okay, we take these two value as the same, okay. If it is not same, you just multiply by a factors, and that factor you just bring it out, right? So make sure they are same, okay, somehow. Okay, so now without damping, the pull would be on the imaginary axis. Okay, so this j omega represent imaginary axis. Okay, without damping, the pull would be on the imaginary axis, and the response would be the undamped sinusoidal. Okay, and because of that, okay, we will start to derive such that by looking at this characteristic, we know that this would occur when a equals to 0, okay, when this become s squared plus b, okay, and therefore from that particular equation itself, okay, we would now note that the pull would be at j square root b, okay, plus minus, okay, so this would be the pulls that we will expect from these equations itself, right? So what is the natural frequency here would be the square root b, this one, okay, square root b, okay, or in other words, the b is equals to omega n square, okay, this is the more commonly used terms, okay. So from this, okay, we will substitute this omega n square into here, okay, into these equations, right? That would be our first part, okay. Then the second characteristic that we would see for an underdamped system would be the pool have two real parts, okay, equals to the minus a divided by 2, okay. How we get this one? Again, we look at these characteristics, okay, equations, okay, we try to solve them, okay, then we will notice that it is minus a divided by 2, okay, by solving without numbers, okay, that numbers is a, all right, so eventually we get a divided by 2, and from there we would note that the damping ratio, okay, the damping ratio is equals to the a divided by 2 divided by natural frequency, okay, meaning to say this, the a is equals to 2 damping ratio multiplied by natural frequency, okay. So by using this one, you just substitute into our equations, and now our equations become in this general form, okay. So we have omega n squared divided by s squared plus 2 sigma omega n square, sorry, omega n s, okay, plus omega n square, okay. So I guess this is again uh, a familiar second order system that you would see in mechanical vibrations, okay, where we start to use the terms called natural frequency as well as the damping ratio, okay. And to solve this one, immediately we have this, okay, solutions, okay, minus sigma omega n plus minus omega n square root sigma square minus 1, okay. So you can see that when we have this form, okay, easily we can solve them into the into poles, okay, by following these equations, okay. So this equation is basically the exact same equations with the root solution for a second order quadratic system, right? So now we would start to characterize, okay, the damping, okay, based on the damping ratio, okay. Again, we have seen the undamped system, okay, the underdamped system, okay, the critically damped, the fastest one, okay, without overshoot, and the underdamped, the slower one, okay, that without overshoot, right? So what is the characteristic of the damping ratio is that for an undamped, the damping ratio is 0, okay. For an underdamped, it's not more than 1, okay. It is in the range of 0 to 1, okay. When it equals to 1, okay, the damping ratio equals to 1, meaning to say this is critically damped, okay, the fastest damping, okay, without any overshoot. Without overshoot means the value should more than the steady state value, okay. The steady state value probably is 1, okay, it shoots more than that, okay. So critically damped will not have that particular overshoot, okay, it just goes straight and to the steady state value, okay. Under damped, over damped will have the damping ratio more than 1, okay. So based on this, okay, we replot it, okay, generally we get something similar like this, okay, very similar, okay, to what we have seen previously, right? So now we can know by looking at the S-plane, okay, the location of the roots, location of the pools on the S-plane itself, we know what we would expect for the output, okay, for a step response. Okay, step response means we test the system with a step input, okay, and how it will respond to it. Okay, so from there we would know that. Okay, the second methods is to identify what is the damping ratio. Okay, so based on the damping ratio range, okay, we can estimate, okay, how it would looks like. Okay, so by doing this, okay, we can quickly uh, identify, okay, whether the system is what we would like to have or not. Okay, so here is an examples of a system, okay, where if you are given a transfer function, something like this, okay, so since this two is the same, then very straightforward, this would be the omega n square, right? Just compare this, okay, 36 would be omega n square, right? So omega n would be 6, okay, and for this value 4.2 would be the 2 sigma omega n, right? So just solve that simultaneously, okay, between these two particular equations, okay, this part and the other part, okay. So eventually the damping ratio would be 0.35, okay. So from 0.35, it is in this particular range, okay, the underdamped system, okay. Therefore, we will expect it to behave in this particular form and have the poles lying on the complex plane, right? Complex. Okay. So here you can try it on your own. Okay. Look at the denominators, the polynomial of it. Okay. And then based on that, you would able to identify what is the damping ratio. Okay. And based on that also, immediately you can know whether it is over damped, critically damped, or under damped. Okay. So you test it on your own, right? Test yourself, all right? Next would be the underdamped second order system. Okay, so this is where we would like to further understand, okay, how the systems behave, okay, for a second order system, okay, when there is an overshoot itself. Okay, so first we need to define the so-called transient specifications. Okay, transients represent when it still not reach the steady state. Okay, we call it as transient. Okay, in the transitions to the steady state. Okay, transient specification associate with the damped response, right? So this is the transient segment, okay, or sections. Okay, next we relate this so-called specifications to the pool locations, okay, and draw the relevance pool and form the undamped second order. Okay, so again you will see that a lot of symbols over here, right? So what we can see is that the transform of the response, the CS itself, okay, which is the transfer function of our second order multiplied by, we expect a step input, okay, 1 over S, okay, therefore we have something like this, okay. So when we try to solve them, okay, we break them into partial fractions, okay, and then since we consider the underdamped case, okay, therefore we set the range of the damping ratio is lower than 1, right? So once we have that in mind, okay, therefore we further expand our partial rate fractions, okay, into this form, okay, then we'll, this turns into this, right? And then take Laplace transform, okay, we'll get this solutions, okay? So you may try this on your own, right? So what we can see here is now, okay, what happened is that when we slowly increase the damping ratio, okay, the damping as we expect, okay, the damping of the system get increased, okay, meaning to say the overshoot will get reduced, and further reduced until a point where there is no overshoot, and further being suppressed, okay, from responding, okay, before it reach the steady state value, okay. So what we can see here is that the lower the value of the damping ratio, the more oscillatory of the response, okay. So if it is lower, then it will have lower damping, so it will oscillate more, okay, before it get damped, okay. So here I try to simulate this, okay, based on the natural frequency of 3, okay. Natural frequency of 3 over here is used, okay. So you can see that the natural frequency is the time axis scale factor and does not affect the natural response of the yeah, does not affect the natural response, okay. What it means over here is that you can see the maximum point over here. Yeah, okay. So it's more or less the maximum point is here, here, okay, here. So you can see that the natural frequency that you would see during the oscillation itself, the point is more or less similar, okay. It will not affect the whole response itself, okay, when we apply the same natural frequency, okay. What would affect the so-called changes would be the damping ratio, okay. For the same natural frequency, we would only see the value of the maximum point get reduced or changed accordingly, okay. But for the oscillation part, okay, the natural response of it, okay, from the time scale itself, they are actually that does not have much effect, okay. They are, we could say they are similar, okay. 3, okay, then over here, okay, over here, right? So they will see that it goes up at the same point, okay, and so on, right? So that is the characteristic of the first thing, okay, the damping ratio, okay. So once we have that in mind, okay, now what we would do is, again, we try to uh, quantify, okay, the response itself, okay. So again, we quantify the undamped system, okay, because there is a overshoot, okay, easier for us to generalize a second order system, okay. So for this quantifications, okay, or specifications of the second order uh, second order system itself, okay, we would use the rise time, peak time, percent overshoot, and settling time, right? So here you would see several new terms over here, like percent overshoot. Okay, settling time, you already seen it previously. Okay, rise time and peak time, you may also roughly get the idea, okay, similar to the previous one, right? So for the rise time, same definition as previous, okay, 0.1% to 0.9% of the final value, okay. So we will take 0.1% to the 0.9%, okay. So we see what is this time, okay. So this is the rise time, okay. For the peak time, we would say set the peak value, okay. Just get the peak value, okay, and get the time, okay. So that would be our peak time, okay. Then for the settling time itself, okay, that refers to the time required, okay, for the transient to be damped out and reach the steady state, okay, since they will still continue to oscillate, okay, even in the probably in the very minute changes or variance, okay. Therefore we set a normally we set in control 2% plus minus of the steady state value, okay. So if the steady state value is 1, okay, therefore if plus minus 2% is 1.02 or 0.98, okay. So as long as the oscillations now, after it reach this point, it will never go out of this range anymore, so we will start to take this as our point, right, as our settling time, right. But for sometimes for a critically damped system, okay, for example, this goes up, okay, then it will go in this way, okay, even though this is a second order system itself, right, and we know that if we follow this settling time, then it will be somewhere earlier, right, somewhere over here, okay. So for these cases, okay, you can either use this one or you can also use this particular steady state values time, okay, to characterize it, okay. So both are should be more or less similar, okay. So this is how you can do the characterizations of these things. Okay, so all these informations again will help the designer to see whether the speed is reasonable or not, okay, whether it would degrade the performance of our system or not, okay. So these characteristics would be used, okay, when we come to the design later on, okay, because when we come to the design stage, we would have a desired target, okay. Normally design will have a design target, okay, meaning to say you may want to improve a system or tune or optimize a system such that it has maybe a settling time faster than the previous one, okay. So from there you must able to characterize, okay, the settling time, okay, or maybe the peak time and so on, okay. So that this would be used, okay, for the design later on, okay, to describe the speed of the transient response, okay, how fast it is, okay, during the transient period, okay. So in order to mathematically solve for the peak time, okay, I may not uh, describe this in detail, right. You just go through this, okay, mathematically, okay, how they can solve it for the peak time, okay. So what we would use here is that, okay, it can be related to the natural frequency as well as the damping ratio, okay. So mathematically you can just follow this, okay, to derive it, okay. And eventually you notice that it is being estimated, okay. The peak time can be estimated as such, okay, for a second order system, okay. The peak time is equals to the pi divided by omega n multiplied by square root of 1 minus the damping ratio square, okay. So these equations would be very useful, okay, for you during the design, okay, to evaluate the peak time, to estimate the peak time, okay. Then we readjust our system, and when we readjust, we would able to know what is the natural frequency and damping ratio, and then from there we can again estimate the peak time again and again, right, instead of plotting the graph, right. So that equations would be very useful for us to evaluate, okay, mathematically, right. The next evaluations, okay, would be the percent overshoot, okay. So percent overshoot basically represent, okay, the ratio between the maximum value minus the final value divided by the final value, okay. So we have the maximum value over here, okay. So it can be this maximum value minus the final value, okay, which is the the so-called steady state value, okay, divide by the original steady state value, okay, multiply by 100%. Okay, so we would know how many percent it have overshoot, okay, from the original target. Okay, so eventually, again, this can be represented or evaluate, okay, by using this equation, okay, related to the damping ratio. Okay, this overshoot mainly depends on the damping ratio only. Therefore, the formula only have the damping ratio. It depends only on the damping ratio, which is E exponential to minus sigma pi divided by square root of 1 minus sigma square. Okay, and since this in percent, okay, so we multiply by 100 so that it is in percent form. Okay, so this is how we can evaluate the percent overshoot. Okay, so what we would see here is that the percent overshoot, okay, when the damping ratio is 0, then this is 100. Okay, when the damping ratio is 1, okay, then the percent overshoot now becomes 0, and it will start at this particular point. It is critically damped, right? Okay, so no overshoot occurs. Okay, next would be the settling time. Okay, again, another way, instead of looking from the graph, would be the equations. Okay, so here is the response for a second order system. Okay, so from this response itself, okay, we can see that to find the settling time, we would look at the plus minus 2%, okay, which is referring to this particular segment. Okay, this is the part that responsible for the oscillations, right? Okay, and we would like this part to be within the 2% itself. Okay, so therefore this oscillation part, okay, but one is the final value minus this particular part, okay, less than the oscillation part less than the 2%. So we will set this part uh, equals to 0.02. Okay, so from here we can again estimate the settling time to be in this form. Okay, minus ln bracket 0.02 and so on. Okay, so this is a more exact evaluations. Okay, but this may not fast enough sometimes, right? Okay, so therefore if we evaluate this, okay, what happens is that we will see that the numerator, okay, on this particular upper side, okay, for the damping ratio ranging from 0 to 0.9, okay, it range from 3.91 to 4.74. Okay, so roughly if we would like to just approximate, okay, without solving the natural logarithm and so on, right? Okay, we can just estimate with 4 divided by damping ratio multiplied by omega n. Okay, this is a rough estimations. Okay, this settling time is very similar to the settling time for the first order, right? 4 divided by the a. Okay, so if you look at the first order system, you have something similar to this, 4 divided by the constant. Okay, and for second order, we just approximate it with this. Okay, but for exact calculations, okay, since nowadays you can easily program your equations in Excel or maybe MATLAB or Scilab, okay, then yeah, no harm, you can use this, okay, for more accurate estimations, okay, instead of the estimations. Okay, this would be useful when you are outside uh, of your computer, okay, where you don't have a computer directly available for you. Okay, so what you can do is you just simply use this formula to estimate. Okay, for the rise time, probably it would be much more difficult because it represent so-called, we take 90% and 10% of the final value, right? So this one, normally it will takes a lot of time, and normally I will not ask, okay, in any of the tests, okay, for a second order system, okay. This generally we will require you to plot it, okay, and get the value, okay, from that particular system, okay. So you can again try these examples on your own, okay. So you just have to find the peak time, percent overshoot, and the settling time, okay. Just follow the equations, okay. First thing, you must able to get the damping ratio and natural frequency, okay. Once you get this one, then the rest would be just plug and play, right? So you would get your answer. So far, any questions?
No, Doctor.
Okay, it's great. Okay, so the last segment, okay, would be the relationship between the peak time, percent overshoot, and the settling time, okay. So this would be important for the design, as I've mentioned previously. When we want to design the system, we would like to change, or to change such that all these characteristic of the transient segment meet our design criteria, right? So if there is a way to relate them, okay, with the locations of the pool, okay, then that would be the best way of it, right? Okay, therefore here is the so-called relationship between the S plane, okay, with the damping ratio and the natural frequency, okay. So from the Pythagoras theorem here, okay, so from the Pythagoras theorem here, okay, this length, okay, remember we may have a so-called complex pool, right? To represent this system would be like this, okay, the underdamped system, okay. So what we would see that the length of this would be represented by the natural frequency, okay. So the radial distance from the origin to the pole is the natural frequency, okay. And then cos theta, okay, cos theta counting from this point, okay, from the real axis negative side, okay, would be equals to the damping ratio, okay. So these two would build up the relationship between the damping ratio as well as the natural frequency. Sometimes it is much more easier to plot, okay, and just get these two value, okay. Or sometimes if you derive it, then there is a chances that it would be easier for you to get the damping ratio and natural frequency instead of plotting the pools, right? Sometimes, okay. So normally the graphical would be the easier one, okay. You just plot them out in the graph, okay, then from there you can estimate, okay. And this by looking at the pools, okay, you would able to so-called estimate the characteristic, and from there, okay, which we will observe later on, okay, we have a technique called a root locus technique, okay. Root locus means we would observe these pools, okay, as the roots of our characterizations equation of the transfer functions, okay, the denominator part itself, okay, how the roots will move, okay, along the locus, and from there we would able to select the proper positions of the roots, okay. And then based on that particular roots, let's say the roots is here, okay, from that particular roots, then we will know what would be the natural frequency and the damping ratio, okay, whether this will meet our desired requirement or not. If not, then maybe the second roots, okay, along the root locus, okay. So that is the word technique, okay. By observing from the graphical form, okay, we were able to design and select the proper one that meets the design criteria. Okay, so here as we can see the ratio, the radial distance and natural frequency would be related, okay, and the cos theta would be related to the damping ratio. Okay, so if we would like to compare the peak time, settling time, okay, since we have the equations, we just substitute all these things. Eventually you can have a simpler form of this, okay, where we have the omega d. Omega d is the imaginary part of the pool, okay, imaginary part of the pool, omega d, okay, this value omega d, right? So eventually this value, okay, pi divided by omega d give you the values, okay. And also for the settling time is pi divided by the real parts, okay, real parts of this, okay, in the negative segment, okay. So we only need the value, okay. So pi divided by sigma d, right? So that is another way of finding it, the TP and the TS from the root locus or the S plane, okay. So that is how we can show it, okay. And these equations also shows that the peak time is inversely proportional with the imaginary parts, okay. So since the horizontal line of the S plane are lines constants, okay, they are also line of the constant peak time, okay, meaning to say that particular imaginary line itself also represent the constant peak time, okay, constant peak time. Whereas for the real parts, okay, it represent the constant settling time, okay, because they are related to the real parts of it. Okay, so now you can see that the peak time deal with the omega d, the imaginary one, okay, and the real one would be the settling time, okay. So this is how it may looks like, okay. Yeah, sorry, another informations would be the damping ratio is given in the cos theta, okay. Therefore this represent the percent overshoot, okay. It's only as a function of the as we know, it is only a function of the damping ratio. Therefore the radial line, okay, and the line of the percent overshoot are related, okay. The radial line, okay, this particular line, this radial line itself, okay, this angle related to the percent overshoot, okay. So three characteristics, okay, of the S-plane being defined by these three specification of the second order system, okay, peak time, settling time, and the damping ratio, okay. So now how we would see, okay, as I mentioned previously, we would come to a stage where we would want to design a system, a control system based on the location of the pool, right? Okay, but before we do that, okay, we just have to get some ideas, okay, how it change, okay, how it would change, okay, when it is corresponding to the S plane, right? So here, as if we have three roots, okay, same real value, okay, but these roots, the imaginary values keep increasing, okay. When the imaginary roots keep increasing, what happens is that it will start from this particular line, okay, change to this line, okay, and to this line, okay. So what happened is that the peak time, okay, this time, okay, and this time, okay, all change, okay. So as we see the poles move in the vertical directions, the frequency increase, okay, because you can see that the peak time shift from this point to this point to this point, okay, per, maybe let's say this is 1 second, so per 1 second itself, okay, line number one only oscillate maybe less than one peak, okay? But then for the line number 2, it will start to maybe we have one maximum, one minimum, okay, in 1 second. For line number 3, we have one maximum, one minimum, one maximum, one minimum, and one maximum. So 3 maximum, 2 minimum, meaning to say this frequency is much more higher, okay? So what we can say that by shifting or increasing the imaginary value, okay, the frequency will increase, okay? But again, the envelope of this still remain, right? So still have the same decaying exponential part, okay, since the real part is still the same, okay? So what we can say from this is that the frequency increase, therefore the overshoot also increase, okay? At the same time, the rise time decrease, okay? So this is the effect of shifting the roots at the same real value, okay, higher, okay, or away from the imaginary, okay, there will have the overshoot increase, frequency increase, and the rise time decrease. Next would be if now we don't not shift vertically, okay, we shift it more to the left hand side, okay. What happens if we shift from point 1 to point 2, the value of the real parts keep increasing, is that from this particular point, okay, or curve or line number 1, okay, the frequency remain the same, okay, because they have the same imaginary value, okay. But what happens is that the peak value now decrease, okay. So as we can say that as the pull move to the left, the response damp out more rapidly, okay, more rapidly, because you can see that it get lower, okay, damp out faster, okay, while the frequency remain the same, okay. And since they have the same frequency, therefore the peak time is the same, okay, they have the same peak time itself, right, moving on the same horizontal line, okay. And the third one is responsible to the radial line, okay. So we can see that there is a radial line over here, right, okay. So if it is moving along the radial line, okay, if we shift the roots along the radial line, what happens is that now the peak value is the same, okay. But what is the difference is that since the frequency, since the imaginary part increase, therefore the frequency also increase, okay, frequency increase. And at the same time, since this is more to the left hand side, okay, therefore the damping of the natural of the roots number 3 or the pulse number 3 will get faster, okay. So you can see that one is damping is lower, okay, then getting higher and higher the damping ratio, okay. So therefore if the pull move along the radial line, okay, you can say that the percent overshoot remain the same, the peak value remain the same, but the so-called the response, okay, is faster, okay, because it oscillate faster, also it damp out faster, okay. So that is the characteristics of a second order and how it would change, okay, when we move the roots from one point to the other, okay, vertically or horizontally or along the radial line, okay. So I think that's all for this, okay. So here is just an examples, okay, on how you may able to use this, okay, to identify, okay, the three range of operations, okay, since normally this K is changeable, therefore we just have to play around, okay, change accordingly of all these values, okay, to obtain the desired response, okay, whether we want it to be under them and so on, okay. So that is how it would looks like, okay. So So you can set the k equals to this, okay, and you would able to so-called get something like this, right? The real and equals part. Okay, so probably this one we will cover more in more detail, okay, in the later stage of the design. Okay, but for now you can just roughly get through it. Okay, just roughly read through it. Okay, after you understand this one, okay, then you just read through it. This one, I guess, nothing much over here. Okay, it will only we will only consider this when we start to do the design later on. Okay, just a brief idea on how they are related with all the K and A's on. Okay, and also you can try to check with these examples. Okay, how we can get the peak time, percent overshoot, and settling time. Okay, for this particular closed loop transfer functions. Okay, another examples. Okay, closed loop transfer functions. Okay, how you can get that. Okay, so that's all for today, okay, and this chapter. So any questions?
Doctor, can you hear me?
Yes.
Doctor, for the next week, the test will be open book or what?
Uh, mm, I think can be open book. Okay, since some of you is online and some of you face to face, right? Okay, you can bring your notes. It's okay.
Okay, so for the test, right? Is it the material same as the inside the example inside the slide? Like
Yeah.
similar? Okay.
Similar. Similar.
Okay, thank you, Doctor.
Okay. Okay. So any more questions?
No, Doctor.
Yeah. Okay. So if no, then we will end this sessions and I will upload this to the Google Classroom soon. Right? Stay safe, everyone, and see you on next Thursday again. Okay, for the lecture before we have the test and the following day. All right. Okay. See you.
Yeah, Doctor. Thank you.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you.